Okay, let's unpack this. Have you ever been faced with a complex technical topic and felt like you needed to grasp its fundamental building blocks quickly, maybe without drowning in, jargon and obscure manuals? Well, that's precisely the challenge we're tackling today. We're diving deep into the foundational world of Dell PowerEdge servers, exploring not just what they are, but how they work, what makes them tick, and the crucial components that, well, truly keep our digital world running. Our unique lens for this deep dive comes from practice questions for the D-PE-FN-01 exam. Now, before you start picturing the exam halls, think of these questions not as a test, okay, but as a sort of carefully curated pathway. They distill years of practical knowledge into critical scenarios, offering us a shortcut to understanding the core principles that IT professionals rely on daily. It's a bit like getting the cheat sheet to what really matters in server infrastructure.
Exactly. And what's truly insightful here, I think, is how these seemingly straightforward questions, they really illuminate significant architectural and operational decisions within server infrastructure. They guide us to the core principles, helping us understand the why behind specific technologies and how they integrate to create resilient, high-performing systems. It's much more than just trivia. It's really a blueprint for effective server management.
Absolutely. So our mission today is clear: to extract the most important nuggets of knowledge from these insights, spark those aha moments, hopefully, and leave you feeling genuinely well-informed without any of that, dreaded information overload. Just for context, the actual DPE-FN-01 exam, it's 90 minutes, has 42 questions, a 63% passing score, and costs $230. But again, you don't need to pass that exam today. You just need to learn from it. Ready to dive in. All right, let's kick things off with something fundamental. How do we actually interact with these powerful machines? Imagine you're an IT administrator. Sometimes you're right there, logged into the operating system, making changes directly. Makes sense. But what about those times when you can't be? What are the key strategies Dell PowerEdge servers offer for management?
Right. Well, for those day-to-day operations when the operating system is healthy and, humming along,
Mm.
most IT pros lean on what's known as in-band management.
hmm
For Dell PowerEdge, the go-to utility here is Dell Open Managed System Administrator, or OMMSA for short. It's designed for comprehensive hardware management directly from within the running operating system.
Okay, OMSA. And for our listeners, what exactly does in-band management mean in this context? Like, what kind of granular control does OMSA offer? Why is it so indispensable when the system is, well, healthy?
Sure. In-band simply means you're managing the server from the server itself through its running OS and its network connection. OMSA is a classic example. It integrates deeply with the OS, allowing you to monitor and configure a vast array of hardware resources. Things like fans, power supplies, RAID controllers, even individual drive health. It's like having a detailed diagnostic dashboard built right into the server's desktop, allowing you to fine-tune settings and check telemetry without needing any separate external tools. It's incredibly efficient for routine maintenance and configuration when everything is operating as expected.
That sounds powerful for when everything's running smoothly. But here's the crucial pivot, right? What happens when the operating system completely crashes or the server is powered down? How do you regain control of them, especially if that server is like in a remote data center thousands of miles away?
That's precisely where IDRC comes into its own. IDRAC stands for Integrated Dell Remote Access Controller, and it's the cornerstone of out-of-band management. It's a completely dedicated, independent management controller. It operates separate from the server's main CPU and OS. Think of it as your server's independent, always-on flight recorder and emergency control panel. Even if the OS is offline hung or the server is powered down, IDRAC is still accessible via its own dedicated network port.
So it's essentially a lifeline then. What kind of critical actions can an administrator perform using IDARC, especially in those emergency scenarios?
Exactly. It's an absolute lifeline. You can remotely monitor hardware health, power cycle the server, access a full remote console to see what's happening on the screen as if you were physically there, and even mount virtual media to reinstall an operating system. This capability fundamentally shifts the cost model for data center operations. Before IDRC and similar tech, any issue needing an OS reinstall or a critical firmware update often meant a costly truck roll,
Right, someone physically driving out.
hours sometimes, to the data center. Now, that same IT professional can manage dozens, even hundreds of servers remotely, significantly reducing downtime and operational expenses. It's not just remote management, it's a paradigm shift in server lifecycle management.
Makes sense. And speaking of critical maintenance, I imagine firmware updates fall squarely into that category. So if your performing an out-of-band firmware update on a PowerEdge server. Is IDRS typically the tool you'd use for that as well?
Oh, absolutely. The IDRT web interface is the standard tool for out-of-band firmware updates. This is crucial because it means you can update vital components like the BIOS, NESIX, RAID controllers independently of the host OS. This ensures critical maintenance can be performed efficiently, regardless of the server's OS status, which in turn ensures continuous availability and security. It's really a non-negotiable feature for modern server environments.
Okay, so what does this all mean for you as someone engaging with server technology? These two tools, OMMSA for seamless in-band management and IDRC for resilient out-of-band control, they provide administrators with incredible flexibility. Flexibility to keep servers running, monitor their health, and perform essential maintenance no matter the situation. It's about having a comprehensive toolkit for, well, every possible scenario.
Right. Having explored how we control these machines, let's now look at what actually makes them tick, the core internal components that enable them to process and store vast amounts of information. Let's start with how servers manage their data, which is arguably their most valuable asset, right? What's the fundamental component responsible for efficiently organizing and protecting data across multiple physical drives?
Yeah, you're pointing directly to the RAID controller,
Yeah.
specifically Dell's PureX or PowerEdge RAID controller. This is a foundational component in server storage, a really key piece. What it does is manage multiple physical drives, whether they're traditional hard disk drives or SSDs, and presents them to the operating system as a single logical unit. Okay, purse. And what are the key benefits of using one? Is it purely about speed, or is there more to it for an IT professional?
It's a powerful dual benefit, really. The Purers not only significantly improve storage performance by striping data across multiple drives, making read and write operations much faster, but it also provides crucial data redundancy through various RAID levels.
Oh, a redundancy. That's the key.
That's where the real peace of mind comes in. Depending on the RAID level configured, if one drive fails, your data is often still safe and accessible, allowing for drive replacement without data loss or significant downtime. This ensures both high performance and robust data protection, which are, as you said, non-negotiables in any critical server environment. The choice of RAID level becomes a strategic decision, balancing cost, performance, and the level of data protection needed for specific apps.
That resilience is absolutely non-negotiable, definitely. But speaking of foundational elements, before any of that data can be managed, before an operating system can even load, the server needs to power on. It's a step we often take for granted, but it's the very first domino to fall, isn't it? In the boot process of a PowerEdge server, which component is typically the first to receive power and initiate the startup sequence?
That's a great question. It gets to the absolute basics of server architecture. The answer is the power supply unit, or PSU. It might seem obvious, but its role as the first point of power delivery is critical.
Why the PSU first, though? Is it just about flicking the switch, or is there a deeper engineering reason?
Well, it's entirely an engineering necessity. The PSU is essentially the heart of the server's electrical system. It takes the alternating current AC power from your wall outlet or data center rack and converts it into the precise direct current DC power required by all the internal components: CPU, memory, storage devices, everything else. And this conversion process, it isn't instantaneous. The PSU must first receive power, perform this conversion, and then stabilize the electrical output to ensure it's clean and consistent. Only after the PSU has successfully done its job and confirmed stable power delivery does that regulated DC power flow to the rest of the server's components to begin the complex boot sequence. It's truly the very first critical step in bringing a server to life safely and reliably.
Wow. So it's not just about turning it on. It's about setting the stage with stable, usable power before anything else can even attempt to function. It's a testament to the meticulous design required for server reliability. Okay, now let's shift our focus a bit. How servers connect, both to the outside world and internally within their own virtual environments. Connectivity is king in the digital age, right? And the choices made here can dramatically impact performance and resilience. When considering network connectivity for a PowerEdge server, especially over longer distances in a data center, what's the primary advantage of choosing fiber optic cables over traditional copper Ethernet?
This highlights a crucial design choice in network infrastructure, a really important one. Copper Ethernet cables transmit data using electrical signals, which, as we know, makes them susceptible to electromagnetic interference, EMI.
Right, noise from other devices.
Exactly. Other electrical devices, power lines, even closely bundled cables. Fiber optic cables, on the other hand, transmit data as pulses of light. This fundamental difference makes them completely immune to EMI.
And what's the practical implication of that immunity, especially in a dense data center environment?
Well, the practical implications are significant. This immunity, combined with fiber's ability to carry data over much longer distances at incredibly high speeds, makes fiber optics the vastly superior choice for high-speed, long-distance, and interference-free communication environments, like large data centers.
Okay.
For an IT professional, it means greater reliability, less troubleshooting for signal degradation over distance, and the capacity for future speed upgrades. It's a strategic investment that pays dividends in uptime and performance.
That's a clear advantage for physical connections, definitely. But let's unpack this further. From physical networks to virtual ones, how do virtual machines communicate with each other and their host operating system, yet remain totally isolated from the external physical networks? This sounds critical for security and testing.
You're describing the core function of an internal virtual switch. This type of virtual switch serves the very specific and valuable purpose in a virtualized environment. It allows virtual machines to communicate seamlessly with each other and with the host operating system they reside on. However, and this is the critical part, it prevents any access to external physical networks.
So it's not a limitation, but actually a deliberate design for specific use cases.
Exactly right. This complete isolation is not a limitation, but a fundamental feature, making it incredibly useful for creating secure test environments, development labs, or any scenario where you need to run virtual machines without them being exposed to the wider network.
Like analyzing malware, maybe?
Perfect example. Or testing new software, building a segmented lab. An internal virtual switch provides that crucial barrier. It ensures that traffic stays contained within the virtual environment, preventing accidental data leaks or unauthorized external access. It's a vital tool for ensuring controlled and secure virtualized environments.
Okay, so from physically robust fiber optics delivering interference-free communication to strategically isolated internal virtual switches containing sensitive virtual environments, servers are designed with precise connectivity needs in mind, offering a whole spectrum of solutions for different challenges. Now let's consider the sheer variety of servers out there. They come in all shapes and sizes, don't they? Depending on where they need to live and what specific tasks they're designed to accomplish. And regardless of their form factor, security at the hardware level is absolutely paramount. Let's look at how Dell PowerEdge servers cater to different environments, starting with maybe the most common scenario for a small business. For a small business that lacks a dedicated server room and needs a quiet server that can sit discreetly under a desk, what's the most appropriate form factor?
For that very common scenario, the tower server is the ideal choice. Definitely. These are the workhorses for environments without specialized infrastructure. They're designed for small businesses, remote offices, or even development teams that need powerful local compute. They look a lot like a traditional desktop PC tower, which means they can sit conveniently under a desk or in an office corner.
And they're quiet, you mentioned.
Crucially, yes. They are engineered for quiet operation, which is a major benefit when they're in an occupied office space rather than a dedicated, noisy server room. What's important to remember is that even in this more accessible form factor, they still deliver enterprise-grade performance, reliability, and expandability. It's all about matching the right technology to the specific environmental and operational needs.
That's incredibly practical for localized needs. Makes a lot of sense. But here's where it gets really interesting. What about the other end of the spectrum? Those massive data centers where space, power density, and cooling efficiency are absolutely critical. How do you maximize compute power in such constrained, high-density environments?
For those high-density environments like large data centers, the blade server is the undisputed champion. Blade servers are fundamentally different in their architecture. They are designed from the ground up to pack maximum compute power into a minimal physical footprint. Instead of standalone servers, you have multiple thin modular blades, each one essentially a complete server that slides into a single chassis.
So the chassis becomes a shared resource hub for these individual servers, like power and cooling.
Precisely. This chassis then shares resources like power supplies, cooling systems, and network connections among all the blades. This shared infrastructure is the key to their incredible space and energy efficiency. By centralizing these components, you significantly reduce cabling, power consumption, and cooling requirements per server, making blade servers ideal for large-scale operations where you need to deploy a huge amount of processing power in a small area while minimizing operational costs. It's a true high-density solution.
Okay, so we've got servers ranging from under-the-desk convenience to those powering entire data centers. Quite the range. But regardless of their size, location, or purpose, keeping them secure is non-negotiable. We agree on that. And that security isn't just about software. It starts right at the hardware level. What's the primary function of the Trusted Platform Module, or TPM 2.0, on a Dell PowerEdge server in providing that hardware-level security?
Right, the TPM 2.0 chip. It's a small but incredibly powerful component for hardware-based security. Think of it as a secure, tamper-resistant vault built right into the server's foundation. Its primary function is to securely store cryptographic keys, digital certificates, and passwords. This capability creates what we call a trusted environment for crucial security processes.
Can you elaborate on that? What does trusted environment mean for the average user or the IT professional managing these?
Sure. For an IT professional, a trusted environment means assurance, confidence. The TPM enables secure boot processes, ensuring that the server starts up with legitimate, untampered firmware and software.
Before the OS even loads.
Exactly. Before the operating system even loads, the TPM can verify the integrity of the boot components, preventing rootkits or other low-level malware from compromising the system right from the start. It also protects encryption processes, safeguarding data at rest. If we connect this to the bigger picture, TPM 2.0 is absolutely vital in protecting servers against unauthorized access and sophisticated firmware-level attacks, providing a hardware root of trust for the entire system. With the increasing sophistication of cyber threats, having this dedicated hardware security layer is, well, it's more critical than ever.
Now, as you think about all these components, consider this just a final thought to leave you with. With the increasing demands of AI, distributed systems, and edge computing, how might these foundational elements from server form factors to management tools and hardware security modules like TPM, how might they need to evolve? Or even be completely reimagined to meet the challenges of an increasingly distributed and intelligent global infrastructure? Something to think about. Thanks for joining us for this deep dive. Until next time, keep learning, keep questioning, and stay curious.